Good evening, everyone. I think it's 5 minutes past 4, and we can start our webinar. So just to introduce myself, my name is Neena Jain, and I am the Secretary General of United Schools Organization of India. Science 101 is a webinar series that's very close to my heart because I was a science student when I was in college. Always had the curiosity for science, but didn't get to pursue it as and on a higher front. So with that, let's start our series of, this is our third webinar in the series, which will be there. It's a series of 12 webinars. So just to inform all of you, this webinar is being recorded and is being streamed live right now on the USO YouTube channel. Links have been shared with all the teachers, and these links can be passed on to the students who are viewing it online and live through our YouTube channel. So just for all of you to know, the mic, the video, and chat has been disabled at this point for all the attendees. There will be a question and answer round at the end of the webinar. Any questions that the students have may please be sent over to the teachers and who can ask them at the end of the webinar. We will open up the chat at that time. So just to give you a brief idea and information about the partners who are actually coming together in order to do this. So United Schools Organization of India, we were established in 1951, and it is our mandate to advance the social, cultural, and moral standard of schools in India to global levels. There's a lot of writing, of course, on this, but simply put, we are the pioneers of extracurricular activities for schools nationally. And we have been doing this since 1951. So that's a little bit about us. I'd also like to take a moment to introduce our partners, CSIR-NISpR. In addition to being our very close neighbors, and I do mean that in physical proximity, one of their offices is, we are next to each other. We also share a great working relationship with CSIR-NISpR. And Dr. Farhat, may I request you to go through the slide, introduce CSIR-NISpR?
Can you hear me?
Yes, we can hear you.
Yeah, a very good evening to all lovely students and teachers. And now on behalf of my head, Dr. C.B. Singh sir, who is heading our Jigyasa and Training HRD division and on CSIR-NISpR team. So I welcome you all. As Neena is telling that we are from CSIR, Council of Scientific and Industrial Research. So basically, NISpR is an organization, our lab, which is very, you can say, young in CSIR. We are the youngest because but we are very old also at the same time because it is a merger lab of CSIR, which has been constituted by two labs which have been merged. One is NIScPR, that is National Institute of Science Communication and Information Resources, and the other one is NISTARS, National Institute of Science, Technology and Development. So basically, about NISpR, what we are doing, we are working towards to make NISpR a think tank globally and a resource center for undertaking science and technology and innovation policy, research and communication. And then we are having a lot of different activities where we are concentrating and doing a lot of work on how we have to communicate science towards the masses. And the best thing is that we are having 19 peer journals, research journals, wherein these are at the international character. And out of these 19, we have three major journals in three different languages like Hindi, English, and Urdu. That is Vigyan Prasar, and then Science Ki Dunya and Science Reporter. These are our three major journals. And the idea is like the young scientists and, maybe the people who are listening, they can also have their articles published in this. So this is basically about the NISpR and Jigyasa, under which this webinar series is going on. This is actually one of the initiative of CSIR among the KVs and the government schools of India. basically Sarvodaya and Navodaya schools, wherein we are just trying to inculcate the scientific temper among the school children. The basic idea is that because the children nowadays, they think that science is a very little tougher subject and a branch because of physics, chemistry, maths, and biology. But the idea is that we have to make science very interesting. So under Jigyasa program, we are doing a lot of good activities, wherein, as I told you, that communication is very, very important. How we are communicating science with the kids, and we thought that at a very lower level, like in fact, from seventh, eighth onwards, we should try to inculcate some scientific temper among the kids by doing some different activities, not just sticking to the books. So Jigyasa is one of the such initiative which we are doing it, and NISPR has done a step beyond it, because with the help of USO, and I'm very, very thankful to Nina, because she has been helping us a lot in like we are now touching underprivileged school children and specially able children also, and we got very good response by doing our painting competitions with the help of USO and many other activities. So my only request to teachers, because I know we all are waiting for Tanvi, and like she will be giving a very interesting presentation right now, which is very, very important. And but before starting our very interesting presentation by Tanvi, I would just like to do two more minutes. I'll just take, Nina, if you allow me. So
Sure.
the one is that I would just request all the teachers who are attending this, and if you can in fact spread this message, that the classroom teaching has to be very, very interesting, and from the lower level, it is very good if you can, add on in your classroom teaching, you can add on some experimental things and some activities which are of our day-to-day life in sync with the syllabus of our students. So, they will not be then scared of what is physics, chemistry, and math and all those things. So this will be a very good thing if you can do that, if you can request teachers to do these things as early as possible, because it makes a hell lot of difference among school kids. And second is like as I told that communication is very, very important. So when a person, when we can make a non-scientific person understand what a science is saying, then I think then you can very well become a scientist. And this is how we all have gone through all these stages. And the step of science 101 is the basic thing what we are trying to do, and it is very interesting, because the scientists at CSIR, they are trying to solve the live projects and they are working on live things. So when we all are sharing our success stories, that becomes very interesting, and the students, they should keep this thing in mind, that how things are happening around us and why things are happening around us. So all these things are very, very important, and this is a small initiative. I think we all will be working towards it. And one last thing I would like to request all is from the students and the teachers is that please go and explore CSIR. If you have pen and paper, write down CSIR. This is Council of Scientific and Industrial Research. We have got 37 labs. We are touching every kind of engineering, what is happening nationally and internationally, from oceanography till aeronautical engineering. You will find a lot of interesting things. So this is from my side, and we are just looking for to see Dr. Tanvi's presentation, where she will be another interesting lecture will be there, and she will be touching like how the water is penetrating under earth and what are the critical zones and all. So it will be a very interesting, I think, presentation, and we all will be learning a lot from her. Thank you so much, Nina, and all the people here. Thank you.
Thank you, Dr. Farhad. That was it makes me want to go and visit the CSIR website, although I've been on it, but I'm always curious, and it's fascinating to learn of the new technologies. So for all those who are joining us today, just to give you a brief about what Science 101 is, we have organized a series of 12 monthly webinars for schools nationally. We conduct it on the last Friday of the month, and what we are trying to highlight are the real life applications of science, which is what we will be doing today as well. Now, the reason and the main purpose, I think we have been through it a couple of times, and Dr. Farhat also touched on it, is to really establish the scientific temper. You see, science is a very fascinating subject. And I say this, I think, in all of the webinars, science is everywhere. The colors, why is, the color of the sky blue? Why is red when mixed with yellow? What does it give you? All of that is science. So it's important for us to keep questioning that, because the curiosity or the jigyasa, and I go back to Dr. Farhad's what she mentioned about jigyasa. So that curiosity is very important, that if we can have it continuously in students. So today's webinar is water in Earth's skin. And I must say it is a very, very intriguing subject. When we think of skin, we think something that is a very thin or shallow layer, but water we know is very deep. So I know it's going to be a very, very interesting topic. In terms of the format, Dr. Tanvi is going to be talking to us about it. We will watch a short video, and after that, any questions that you may have, or the students that may have, they can post it through their teachers on the chat. So our scientists and I have the pleasure and the honor to welcome Dr. Tanvi Arora, and she will be talking today about water in Earth's skin. So Dr. Tanvi, before you start, I'll just take a moment to sort of go through your fabulous and very impressive achievements. So Dr. Tanvi joined CSIR-NGRI. NGRI stands for National Geophysical Research Institute. She joined CSIR-NGRI in 2008. And she's interested in the application of electrical resistivity, the self-potential, and induced polarization. These are words that I remember and recall from my high school and my bachelor's degree, but it did bring back lots of memories. And what's fascinating is that Dr. Tanvi, using these means, tried to address a variety of problems, which includes the contamination of aquifers, time-lapse measurements, and so on. Now, Dr. Tanvi is the recipient of the Amity Young Researcher Award in 2019. And most recently, Dr. Tanvi was selected for the Craig J. Beasley Award for social contribution from the Society of Exploration Geophysicists, which is the SEG USA, for the year 2021. Now, she is, in fact, the first, am I not right, Dr. Tanvi, the first Indian to be selected as part of this award. In addition to that, she's also the first scientist from India who's receiving the award from SEG, and she's also inducted as a member of the Scientific Board of UNESCO IGCP program for a term of 4 years, which is from 2020 to 2024, because she has worked on several projects of national and international repute. These projects, several of these have been sponsored by UNESCO, the European Union, the government of the Republic of Niger, and several others. So, really an honor for all of us to be hearing from you, Dr. Tanvi, and very, very happy and excited to know how is water Earth's skin and not something deeper. So, Dr. Tanvi, please.
Yeah, thank you, Ms. Jain. And it's a wonderful time for me to be here among all the big people. Ms. Farhat is here, then Sumanji is here, and USO is doing very good. When I got this invitation, then the first thing which I did was Google. So I just Googled it, and I was really amazed to see the type of reviews your organization has got, and you are doing a commendable job towards upliftment of students and science in the society. And I'm really feeling good to get connected to so many schools. I could see like there are more than 35 schools who have joined and still joining. And I must say, like, one teacher counts to almost 1,000 students. They take up the things and they get connected to so many students. It's really a big job, and I will try to justify this next 1 hour of my talk, or so that students and the teachers may get benefited of what we are doing. Already been doing a lot of things in scientific research and policy research, and Farat ma'am has listed out about the activities of CSIR. So I would also start from, okay, can I share my presentation?
Yes, absolutely, Doctor.
So I think it's visible.
Yes.
Yeah. So I would also take you to the journey of a certain different aspect of CSIR. So I am based in National Geophysical Research Institute, which was established in 1961, and recently we did our Diamond Jubilee celebrations in 21. And we do pursue research in multidisciplinary areas of highly complex structures and processes of the Earth system and its subsystems. So we work on a different aspect of exploration of natural resources, which includes water as well as minerals. We also do a study about earthquake and tsunami studies. And overall, we look into the Earth system to understand its geodynamics and various processes about the evolution of the system, and how long it will sustain and what will be the consequences of different things happening in near future or in long run. So basically at our institute, at NGRI, we have 7 major R&D activities and groups which expertise into geophysics, geology, geochemistry, which includes seismic methods, electrical methods, gravity and magnetic. Then we work on electromagnetic principles to explore the shallow surface and the deep surface, deep subsurface of the Earth and its happening processes. So we are always, since more than 60 years of establishment, our institute is committed to address the challenges of near future and near surface, to bring benefits to science so that the impact on societal priorities can be visible and can be worked out towards finding the feasible solutions. So the topic I'm going to start is water in Earth's skin. As Miss Jen said that skin is very superficial, but then water is deep. So I would, through my talk, through this small journey, I would like to try to link between the skin and the water, which is like skin is on the top and then water is down. So what is there in between? This I would like to try to explain and see how far I may go ahead. So when we talk about water, so immediately things comes up: rain, contamination, aquifers, lakes, groundwater. So all the terms which you can see here, you know. So okay, so all the terms which you can see here, it clicks very immediately, even to a layman it clicks. And then if we argue, we inquire a little bit deeper, then we can say pollution studies, how it comes through sewage and industrial waste, and then how the cycle is affecting the climate change. Or people do talk and take interest in soil science, like how the agricultural produce is being done and how water is being used. Or the very simple, which we are being told since class 4. I think since standard 4th, we are being taught about the hydrological cycle. So these things come up to us very quickly, and we are well versed with these terms. And to an extent, now we are also aware, our society is aware about the footprints of water, like how much amount of water is being used in making a masala dosa. Just one piece of masala dosa, it requires 683 liters of water. Or for an omelette, it needs 789 liters of water. And then for a tiny piece of samosa, 69 liters of water is being consumed directly and indirectly. And then for chole bhatura, it's everybody's delicacy, and we all love it, and it requires 653 liters of water. But as a normal person, we hardly drink 3 to 4 liters of water per day, except for the students who are from the sports background or who are very much involved in the physical exercise. They may consume little more, but as an average human being, maximum 2 liters per day is enough. But see, indirectly, when we eat such things, we are making this water resources spend so much on us. Then comes this hydrological cycle. Everybody is well aware. So I'm just trying to brush up few things to all of you. So this is the hydrological cycle, and what we do, everybody knows. Then this is a river flowing, and then evaporation or transpiration happens, and then this moisture sits and meets the clouds, and then they change, they become heavy, and we have again rain here, and this water goes into river. But see this part, from where it is coming, there is no link. This water which is coming from mountain or this green slopes, so it is going into river, but in this zone we couldn't see any link here. So if we see little bit on a tinier scale, then this is our soil, and when rain falls, so the top soil, it absorbs water. These tiny droplets in the form of moisture are being absorbed by the soil, and what happens next is it converts this, further goes deeper down from the top, little bit deeper down, say a few centimeters or say a few meters. And when we have this life, this is the zone where life is being produced. We do the seedlings, or the life happens here when this water falls and it penetrates down. But what next? What is next to it? So if we see in total, this is our earth, and if we cut a slice of it, see, like similarly a watermelon, and we cut a slice, we see different layers, green, white, and red. So our earth's internal structure is also like that. It's atmosphere, crust, mantle core, outer core, and inner core. All of you know. But this zone, the top few meters where all this green belt is happening, where we are standing actually, where we are breathing. So this zone, which starts from this top of the tree to the bottom of the water table, if this small part is cut here, then the top of the tree, just assume the mango tree in your school campus, and it starts from here, goes down, further down where this life was happening, the seedling was growing up, and then little bit more deeper where we have this water table. From there, here this water comes. So this zone, this complete zone is called the critical zone, and in terms of scientific language, we call this as the skin of our earth. So it's very thin, but it's very complex. Like for the biology students, we have 3 different layers of our skin. The top layer, which protects, which acts as a defense. Then the second layer, which has all the tissues and the collagen into it. And then the third one, which stores the fat to supply to the body. So it is in the similar way. This is our defensive zone. This is the collagen producing zone where all these roots, capillary action, transpiration, then all the suction force for the moisture from up to down and down to up is happening. And then this is the water table where the water is the necessity for everything which is happening above, including us. So this is being stored here. But the question comes, how can we see this water table? Once I happened to ask this question to students that from where you get the water, and I got very funny replies. They say, we get it from the tap. Well, quite obvious. Everybody gets the water supply through tap. Then somebody says that we put on the motor and then we get the water. That's also fair enough. So because many houses where we don't have water, many places, especially in metros, where there is no continuous supply, so we need to rely on the pumping motors to pump the water. But had anybody thought that from where into the tap or in the pump, from where this water is coming? So this part which is below our Earth's, below the subsurface, is where water is stored, is called aquifers. And it is not continuous. Our society, many people have this thing in mind that aquifers are continuous, they are never ending. So whenever we want water, we will just put up the pump, we will drill the well, we will put up the pump, and we will start producing the water. No, it's not like that. So it's, in fact, these aquifers are very limited resources. They are like the bank balance. So unless you deposit some money, you cannot withdraw. So now we all are aware that water is running out. So we need to put more stress on recharge. We need to make rainwater harvesting pits. So that is a type of input we have to give to this resource. Then only we will be able to get the sustainable supply. But again, the question comes, where are these aquifers and how to study them? They are not continuous. They are in patches and in different medium. From visible sources, if we see the Ganga belt or any river belt we see, then we will have not many hand pumps there, and we can dig to certain depth and get the water. But in terrains like rocky terrains, if you been to the south part of India where we have hard rocks, even if we go 300 or 400 meters, we don't get water. So they are quite deep. Feet, maybe 1,000 feet or 1,500 feet. Even if we drill, we don't get water sufficient. So why this variation? So I will not go into details, but as a geophysics is nothing but geo and physics. So let us make it simple. Geo means earth, and physics is, all of you are studying physics. So when we apply the physical principle to study the earth, that is what geophysicists are being made up. So we have this ability to see below the surface where we are standing. We can see deep down. And just to explain you one of the models, see, this is a river, trees, and below that, this blue line is a water table, and we have some groundwater resources, and then we have different things, maybe sand, gravels, clay, or bedrock, or some rock. This is what we call geology, or about the interiors of Earth within the skin. But what about how to explore these things? Actually, we cannot see. So our Earth is, and this is a real picture. If you might have seen the tree with this root expanding deeper down, then propagating in horizontal and vertical direction in all complex media. They all need water to survive, and they are sometimes very deeper than maybe 200 meters deep, or 223.5 meter deep is the maximum thickness of this zone which is existing worldwide. But the question comes, when it rains, where does this water which falls on this rock or this soil, it goes? It's very easy to see कि मिट्टी ने सोख लिया होगा, लेकिन उसके बाद भी तो नीचे जाएगा because of gravity and other forces. It has to go deeper, but where and how? And how these soils are being formed. This is again a very important part of our critical zone. As we say, how our skin was being formed medically and biologically. Then burning questions about the forest, the ecosystem, how to make a balance about these things. So all this critical zone science, which we are trying to explain the complexities of this Earth's skin, like from the top of the tree to the water table, that is one of the part of study what we as geophysicists are doing at our institute. And globally, people have worked about it. If you see this map, then the thinnest zone of this critical zone, or the thickness of the skin, was found out to be 0.7 meters, 0.7 meters. So it is very superficial. And the maximum thickness of the skin was found out to be 223.5 meters. So there is so much of variation and heterogeneity. So we cannot say that, okay, we cannot generalize things. Nature is complex and our Mother Earth is even more complex. So now this was a brief like about what is Earth's skin, what is critical zone science, but this was to generate some exciting questions among students. But now what as a scientist, what as a researchers, we use the technology available with us, and how do we explore this zone? Geophysics, as I told, it is geo plus physics. So when we apply the physical principles to geo means earth, then that study is called geophysics, and it is an intersection of geology, physics, and maths and computer science. So it doesn't mean that we just do some testing and get the results. No, because whatever is down, it's not known. We need to explore it by doing a lot of modeling, by doing a lot of mathematical calculation, and then using the properties by geology, applying what physical principle is being used. If just to simplify it further, when our medical doctors perform some X-rays or MRIs, then this type of negatives or this type of films we get, like this is MRI scan, and then this part is from pregnant women where fetus is being shown, and this is again about the bones which are being shown as an X-ray, and it is the capture of the internal structure of human body where different parts are being shown. So what doctors do, they send some rays into the part of that defective part or broken part of the human body, and then when these rays penetrate, we got a film, and that is what we call X-ray or MRI scan. Similar way, we are also the doctors of Earth, and we do the similar things. But the problem is our human body is, we can see round. That's why डॉक्टर बोलते हैं ना ऐसे घूमो, जोर से सांस लो, ऐसे करो. Same way we are handicapped in that way. We cannot say because layer is fixed. We cannot ask Earth to rotate so that we can see a 3D view. But we do the same thing, and then we have to identify where the problem is and how it can be solved, how we can come up with these things. Now, smaller the approach. Suppose if we want to identify some water problem or water resources within Delhi, it's fine. We can cover up the whole city in 2-3 days, and we can identify the sources and see where the problem is existing, how where it is broken or where it is fractured, or where the soil zone is contaminated, where pollution is happening. But if suppose we have to do this analysis for all over India, then it becomes a challenge. So we have different methods by which we can study even the microstructure. We have in this microstructure, what happens? Smaller the area, bigger will be the resolution. We can very confidently say that, okay, this is just one room of study, and we can analyze properly what is the depth of soil and what is beneath it, and how the trees are transpirating the water. But if we have to see on a bigger scale, then we have to make use of different geophysical methods. So these methods we call as hydrogeophysical method, where we target to identify water. Now geophysics was geo plus physics, and when we add the word hydro, so hydro is water. So when we apply physical principle to study Mother Earth or the Earth's surface with a target to identify water resources or water-based issues, then these methods are called hydrogeophysical method. And on a smaller scale, we will have good results, good confidence, but we do well logging, we do surface imaging, and even the latest technology which our institute is using is identifying the potential zones or not contamination, but potential zones and aquifer orientation by use of heliborne surveys. So that is for covering a vast study area. So various methods. Maybe now it comes to your class of studies, especially 10th class students may be aware of the electrical methods, which includes Ohm's law, where we have some controlled current, and then we have controlled voltage, and we measure the resistance, or it's other way around. We know some log of specific resistance, and then we send some current and we measure the voltage difference across the two ends. So the basic science is same. Whatever we have studied it from class 8, 9, 10th, and 10th, that principle will not change, but its application, the complexities, that is more demanding, and that's where the research takes place. So electrical methods are being used. We have induced polarization method, where we have the different zones of different conductivities. Like suppose in some area of your place, the water is salty or saline, especially along the coast. The water is saline. You cannot drink the sea water. It has high amount of salinity into it. And this aquifer exists in many coastal areas. So how to differentiate? We cannot pump everywhere, but if we do this IP methods to do the survey, if we use it, then we can identify where sodium is high or sodium chloride is high and where it is less. Similarly, we have self-potential methods. Now, if we have some on mountain regions where the water table is not straight, where the aquifer is not straight, but it will move along the topography. The hill is slant and water table will also be slant. So to see in which direction it is moving, whether it is more horizontal or more vertical, then we use self-potential methods. Similarly, we have different methods. Mislamas is again if there is a fracture. So when there is a fracture in patient's hand or knees or legs, then we go for X-ray, and then doctor may ask lumbar X-ray or with different angles. So Mislamas is similar way. We use this survey or the methods with different orientation. Then magnetic methods. Suppose we have some iron ore or some mineral based methods. So we use magnetic methods because they have the affinity to get attracted to the minerals present. Or for digging of gold, we use magnetic methods at our institute. In fact, for identifying the diamonds, we have used electromagnetic methods as well, and magnetotelluric methods. Then gravity methods. Gravity is similar with the push and pull of gravitational force. So there is some contrast. Gravity pulls with the same value, but kuch material aa jata hai, kuch nahi aata hai. So when this contrast is happening, so this difference on the density, we can identify with the gravity methods. Then seismic methods. All of you might have heard about it, seismic methods. And we do use seismic methods for groundwater, for minerals, and then also to see the oil and the gas fuels within the country and the worldwide. So there are a lot of methods. It depends, and the basic principle is same for these methods, which we study either in 10th or 12th or graduation, like Ohm's law, Snell's law, Maxwell's equations. So physics is same. How we use it, I told you, like this Ohm's law, we use it because there is a certain amount of a log and with a fixed area of cross section where of length L. Then if the resistance within this log is R, then the resistivity can be calculated. We work basically on resistivity, which is directly proportional to this resistance developed through the passage of current and this cross-sectional area, and inversely proportional to this length of the log. So this is the basic parameter which we measure. Now this is the case of a straight line, but in Earth we don't have a straight line. So what we do, we send current at two different rods. These are called electrodes, which we place it on the surface, and we send the current. With this current lines propagate in different forms, in a hemispherical forms from source to sink, and then After sending current, a resistance is developed, and we measure this potential difference at these two different electrodes again. So this is again not a even case. How we do it? We put it on the surface, all these rods connected to some battery, like you have inverter batteries in your home. It's not the same way, but the specialized one. And then we plug in positive, negative, send the current, measure the potential difference, and that's how we interpret. Okay, this can be this zone, this other one at deeper depth, say at 5-meter depth can be this zone, 10-meter depth can be this zone, 15-meter can be this thing, say so loose soil hai, pebbles hai, or water hai. So at certain depth we come across, through this measurement of current, sending of current lines, we come across the identification of water. Now, how do we do it? Okay, so how do we do it in this in the field, in the lab? This is a workout, so I'll skip this. I'll just directly take you. This is a small instrument with which we send the current. This is the battery, and then the cables which we lay down in the field. So I'll take you to this thing. Suppose if we cut a part of earth into as a cross section, you see the grass, and then this soil and loose sand, or somewhere deeper we may also see some water. So what we do with this electrical resistivity method, we can see, we scan it. Now we put all these 4 electrodes, these 2 through which we send the current, and these 2 through which we measure the potential difference, and we continuously tow it away. So we don't do it literally, but the instrument does it. But to explain that, it scans total. It scans total Earth surface, and we get different values of potential difference at different ends. And at the end, when we, so this is the difference. These are the electrodes which you can see. These is steel rods, and this is the cable with which they are connected. And this is how on the surface, on the ground, this looks like moving. So moving literally doesn't mean that we take up and then move, we take up and no. We just lay down this whole profile and see how it is scanning below. Same way, आप लोग ECG कराते हैं, तो doctor puts different clutches at different points, hands पे लगाते हैं, legs पे लगाते हैं, and then आपके body के different parts पे लगाते हैं, and then they send some pulse. So we also do it in the same way. We lay down the cables, and then we send some current pulse and see what is beneath it, what is inside it. If there is some abnormality or some fracture is there. So we do it in the similar way. The process is same, technique is different. And what we get the result? We don't get X-ray film, but we get some colored beautiful pictures in this form. Now let me try to explain you this. This was the place where we laid down the cable, and by putting it here, we laid it up to almost 100 meter, and we got the information up to 20 meter below. So just imagine your house, or maybe from your house or from your school, from your class till your main gate of the school, maybe around 50 meters, or say 50 or 60 meters, I don't know, but can just cut it. So how far will be 20 meters like this, and then just tilt it. So below the surface, below the ground, if you can see 20 meters, it's wow. So everybody will be happy ki kya hai niche, we will just take it out and dig it out. But this is what instrument does, and then the job of scientists and researchers come into picture. We have to identify what these colors indicate. So in general, this is a resistivity map. So this low resistivity, which is blue in color, we correlate them with the water, and this high resistivity, which is red in color, we correlate it with the boulders or some stones or some material through which this rays cannot pass. So these are some benchmarks, but it varies from place to place. Maybe at this particular zone, we have up to 20 meter we got water, but at some place we may not get. So I will show you some these things in detail, how we can see over a time all these points. So what we did, we carried out some experiment within our campus. So this is our NGRI campus, and in South India we have beautiful dug wells where you can just go down and see what is the structure of water and how far it is, and then you can also see the critical zone, the soil profile, which is quite open. And in north part of the country they are not very easily visible. So what we did in our campus, we lay down this resistivity cable profile at 2-3 places to see how with time, you know, during the rainfall the soil will be all wet, but in summer soil will be all dry. So again, that is why we face the problem that in summers we don't have water. We have water scarcity at many places. All hue and cry is there because soil is dry. If soil is dry, how it will reach down? How water table will be getting recharged? So we did this experiment to see, or in all the, after every 15 days we repeated the measurement. We laid down this profile, and after 15 days we were trying to see this colored beautiful picture where the water is and how it is moving. So after some time, so this is again some lithology thing, which I don't think that I should explain it here, but we also correlate these colored zones with some weathered zone or laminated granites, which are geological terms. And why they are useful? Because they exist globally. It's not only in India. They are like the universal lithology which exists globally. So as they are like benchmarks, they are standards. Okay, if this lithology is there, then this should have this. Some fracture should be there, or water producing zone should be there, a bedrock should be there. So I will show you this one small movie where within our NGRI campus, we carried out this experiment with time. We started from monsoon of 1 year and ended at the same time of monsoon, in summers next year. So just observe it closely. Just observe this zone and this zone. Initially it is green, and at the end of the movie or at end of this experiment, how it is changed. The movie or at end of this experiment, so did how you it see changed? That in the starting this part was slightly red, and it remains total red at the end also. So it means there is no water disturbance. There are stones which are fixed and no water or so moisture is taking place. But at this zone, this was initially green, and it has turned to be blue. And this part, which was blue, experiment, did you see that further? In the starting, this part similarly was in this red, part of the area remains total red. So what at the end also when rainfall occurs, when there is no water disturbance, all the water which are fixed and no roads, water or so moisture is taking place. But at this zone, this was initially green down through this, and it has turned to be blue. And this part, which was experiment, did you see that in the starting this part similarly in the part of the area remains total red at the end also. In this case, so it means when there is no water disturbance, all the water which are fixed and no roads, water or moisture is taking place. And this zone, this was initially green down the natural, and it has turned to be blue. And this part, experiment, did you see that in the starting this part similarly in the part of the area is the process? What happens when this adding up all the there is no water disturbance, all the water is being fixed and adding to the contamination in the aquifer, and this zone, this was initially green, then we know this and it has turned when we divert this part in natural experimental conditions, then we are starting this part similarly in this part of the so this is the process that what happens when this adding all there is no water disturbance, all the water is being fixed and adding to the contamination in the aquifer, and this zone, this was initially green, now we know this and it has turned when we divert this part in natural experimental conditions, then we are starting this part similarly in this part of the so this is the process that what happens when this adding all there is no water disturbance, all the water is being fixed and adding to the contamination in the aquifer, and this was initially green, now we know this and it has turned it was strong. All over, then we cannot have the resource. We cannot have sufficient supply. And this is, we don't know. We can identify. So this is very important. We also measured the soil moisture along with it at particular depth, how the variations are going on. And this work is published in Journal of Applied Geophysics. Maybe the teachers, if they are interested to pursue further, because I am trying to explain it at a very, very simple language so that students may get the crux out of it. But if you are interested to have some questions further, then you can read this article and I would be happy to be contacted again. And then we also did some statistical experiments and analysis on these data sets, and that's how we got the results. So all this is explained, and finally we established a relationship between the soil moisture and the resistivity, like how it's moving, how the soil moisture is moving at with particular depth, and in what way resistivity is behaving towards that add-on. So at a point of time till it becomes fully saturated, there is a linear correlation, and after that it becomes uniform. There is not much change of resistivity as well as soil moisture. So we did experiment in the real field, which I have shown you, and also we took the samples and brought in our lab, and we did in oven, we desiccated it and dried it, and we found out the similar relationship. So it's well established, like after 13% of moisture, there is not much change in resistivity as well. These are again some snapshot where this is for another site where we did opposite experiment. Like we were pumping the water, and how with pumping the zone was becoming drier. So there it was becoming wet. As you saw, the color changed from green to blue, but here it changes from blue to red. So it was a different experiment, but it just worked fine. Then we did some study in Raipur area where the geology is different. So we have karst aquifer system. Karst aquifers are basically the systems made of limestones, where you might, I think in 9th or 10th, students might have heard about stalactites and stalagmites, where we have caves formation, and out of the water dripping from down, and then their chemical composition, those stalactites are formed. So that system is called karst aquifer system. And again, if there is a cave, we can go and see. But if there is no cave, how to find out that whether there is water or not? So this was the area in Raipur. We have a local drainage nala system called Chokra Nala. And what this was a small area of 5 kilometer, say 10 kilometer by 10 kilometer square area. And the beauty was that we had a nala here, very big nala. And the objective was, there is a drainage. This nala was here, but there were some recharge structures also. But the government wanted to know whether these points, these locations are really effective that water is going down or not? No. So they have made a structure, but without any scientific knowledge, without doing any geophysical surveys or methods, investigation. So we went there and did some resistivity points, electrical resistivity points, and this was the depth-like structure which we got. Again, if you see again that beautiful red to green and blue type of profile. So here it is different. See, this red zone is very big here, and this is all dry limestone. It's very hard, and its resistivity is also very high, almost 800 ohm meter. So in this zone, there is no water. It clearly shows. And in the top part, it is blue, so it was low resistivity. So the water was lying on the top. But we wanted to know whether some fractures are happening. कहीं कुछ cut है जिससे कि surface का पानी नीचे चला जाए. So we wanted to explore that zone here. So what we did this survey again. This was a big profile, double of the previous one, almost 400 meters, and we could see up to almost 55 meter below. So that previous one was up to 20 meters and this one was up to 50 meters. Now the question may come, how we can spread it? So the bigger the profile horizontal is, that wire and cable system, we can see more deeper information. जितना बड़ा प्रोफाइल होता चला जाएगा इलेक्ट्रोड्स का, उतना हमको नीचे का इंफॉर्मेशन मिलेगा. But it has to be in a straight line. So maximum we have done is almost around 2 kilometers long profile, which our institute and my colleagues have done. So I have also done up to 1.6. So it was in breaks. So bigger the profile along the surface, more deeper we can see. And here we did this, and we located some points for drilling activity. We have a point where this layers were dipping down, and we could identify the location where this part was partly filled with water. So this light green zone, this little dark green zone was identified as partially filled limestone, but no sources of getting water into that. Similarly, at another point we did, and we identified a big gap here. Again, this is a limestone here, and this can be probably a cave, where some stalactites or stalagmites may be found out. It's not sure, but we have a wide gap of very, say, 300 or 250 ohm meter of resistivity, which is not very high as compared to this contrast 2000. So this is very strong boulder, and this is very mild formation, which is not water, of course. But then when we drilled, we find out that this top few 13-14 meters has some potential things where water recharge may happen, may not happen, may happen. So we did it at many places, almost like we did correlated it with some logging tools. Logging is what when we send some sensors, so it gives a count of nearby places. So we did that as well, and it indicates some correlation with the presence of some limestone here. And this, you can see, these are the real samples, real soil samples or pebbles which we got after drilling, and this is how we prepare the litholog after identifying. And this gives us an indication about the continuity at different places. Like we drill at one place, suppose in DPS at one point. I'm not very much aware about locality, but say one we drill at India Gate, and second we drill at Chandni Chowk, and third we drill at Lajpat Nagar. So how to see the continuity among it? So we prepare this litholog, and then we connect them all together. These layers, we connect them all together. And this is how we come out with this layer cake model. We can see overall, okay, so at this whole area, these are the points. And based on these models, we can say whether the zones are fair conductive enough to get the water intruded, or they are resistive enough to get into the system. So this work is again published into one of the publication in Journal of Earth System Sciences, where if teachers are interested, I would be happy to discuss further. But it's like we do the survey, we drill the wells, then we connect it all together, and then we see how the formation is spreading all over the area. This and based on that, we did give our inferences to the Central Groundwater Board at Raipur, and then they have changed the location. Earlier proposed location was finding out here, but then they changed it to some other location in conductive zone, and that's how it worked, and people were really benefited. But in one interesting thing was there in karst system when we drilled wells. So maybe in below, after drilling at certain depth, due to the pressure, I am not sure we encountered the cave, but there was a pressure of water flow and our well collapsed. So that was also an interesting thing to find out, okay, what can be the reason? And that answers we have got after drilling. So if teachers, I request you to go through this publication, and you will find it more interesting how we have correlated it further. And I'm sure you may have some burning questions as well. So next, third thing, what we did is in crystalline formation or in granite rocks, we have done a study to see whether the water is going down through tanks or not. So this is a general convention that if there is a lake or some storage tank or a percolation tank, then that is the main source of water, and below that there will be a lot of aquifer, and in that area or in that village people will never face water scarcity. So this is a nomenclature in layman's language, in layman's mind. Even sorry to say, but many of the policymakers also think that okay, if there is a lake, definitely water source will be there. But when we carried out our scientific investigation here, so this is a crystalline aquifer is like a hard rock. It's like granite basically. So in South India, we have a watershed nearby to our place of research. It's called Maheshwaram. And there was a tank here. Tank means it's like a storage tank, जैसे हम तालाब बोल देते हैं ना, बड़ा तालाब था. So we did our profiles in different orientation along this tank and then crossing it in oblique to it. And what we find, and this work was carried out as a European Union project called SAFPANI. If you can see this, then there is a website and all this study material is also available. So what we did it that we carried out the profiles, and again you can see just by seeing the color codes you can identify, oh, this blue or purple color means highly resistive. The water cannot go there. Just as a layman, just as a there is no science behind it, just with this color code. But when we put it in the proper fashion, we could see that there is no space, there is no soil thickness, there is no critical zone. And below this tank, after a depth of say 25 meters, or this is up to 30 meters. So after 30 meters, or here it is 20 meters, this is the scale. And after 20 or 30 meters, there is totally hard rock. It is all solid rock. So how water will go down? So this is a very big misconception at many places where we don't do the scientific investigation and we think, and क्या होता है, बारिश में पानी भर जाएगा, थोड़ा पानी रहेगा, but this is not a sustainable measure to see the efficacy of the aquifer system below this percolation tank. So we have presented this work to the policy decision makers as well, and then many initiatives are being taken in Telangana and Andhra Pradesh. So again, to show you one more application in basalt terrain. So basalt type of terrain, they are formed by the lava flows. If you have been to Maharashtra, then Mahabaleshwar, the picture is sketch, and we have different lava flows. So when lava solidifies and this type of stones, this type of rocks which are formed, they are called basalts. Thick, very thick and black color of terrain, very solidified. So we did some work in this part of Tapi River Basin where it was all basalts, and this is Satpura range of hills in Madhya Pradesh. And then what our objective was ki when it rains during this monsoon season from this hill area, when it rains, the intensity of rainfall is very high. It is amazing. Like if we see the parameter ki barish zyada ho rahi hai to pani ka problem nahi hoga, so that type of concept. But what was happening in reality, when this rain was happening, rain was falling down, this part of village was not getting water. So the objective of this project work was to see that when this rain is happening due to this steep slope, water is just flowing down. It is not going into the Tapi River Basin, and below which resources are not happening. So we were given a responsibility to identify some place where we can tap this rainwater. We can say, okay, this is the zone. अगर जैसे छत का पानी आप लोग इकट्ठा करके नीचे डाल देते हैं pits में, so it's not that same concept, but if we collectivify and then divert this rain water into some pit, then the aquifer may be getting benefited. So with this concept, we did again the beautiful blue and red color of profiles, geophysical profiles we did, and we did a lot of analysis and different orientation. There were more than 35 ERT resistivity profiles which we did. And at the end, what happened? So this was the longest one I was telling you, almost 2-kilometer long profile of resistivity variations. And what we identified that in some particular zones, we could see that this blue part, it is a potential zone for recharge, it is existing, and it is quite thick. It is quite thick of say 60 to 70 meters. So what we propose that in this village, if due to the rush of water, if we can create some barrier or some structure here, so water can be tapped through this zone, and it can in turn enhance the aquifer storage, and we can avoid the runoff from this hilly terrain or runoff through the basalt zone. And again, this work is communicated this year in applied geophysics, but I can provide more details if required. So this was a sponsored project of Ministry of Water Resources, and we have recently finished it. And this zone, out of the whole area, this zone was identified as the most favorable site for recharge, like based on the soil thickness, critical zone thickness, and the resistivity below it. So we could locate and propose some things to them. These are some field photographs at different places, Kerala, then Tamil Nadu, then Maharashtra, and we did sampling as well. And when you got success, you drill the well and you can see what is inside it. So that is a real happiness being in field geophysics. And with this, I really thanks NISPR and USO for inviting me here. And I hope that a part of my presentation was conveyed properly to the students. Thank you. And I would be happy to take some questions.
Thank you very much, Dr. Tanvi. That was very, very insightful. This is how we come to know the real life applications of science. It's not a subject that is just studied, but it is also a subject that is used widely. So very, very interesting indeed. I'm just going to take a moment and pull our presentation out. Now, in terms of questions, teachers that are on the call, I'm just going to open the chat box. If you can type in the questions there. Then Dr. Tanvi can can take the questions. From your voice, Dr. Tanvi, it was very evident that you love the field visits and doing the experimentation. I think that's the most exciting part. Even as a student, I think, and for all students, it's that's the best way for them to learn as well. When we are doing the experimentation. So just to let you,
Earth
sorry.
is, for a scientist, it is a pleasure to be in the lab. Whether it is chemist or biologist or whatever. And for us as an earth scientist, so Earth is our laboratory. So unless we go there, we cannot get the feel of the data. That's very important, to be in the field when you are into this type of job.
That's right. That's right. So teachers, if you can kindly ask, the chat box is now open, has been enabled, sorry, not open, but it has been enabled. So if you have questions, please type it in the chat box. Yes, this recording will be available and we will be sharing the link. It will be on our YouTube channel and the link will be shared by tomorrow. So Harsh sir, this just to let you know that the recording will be shared. Dr. Tanvi, there's a question. May I read it?
Yeah, I could see it. Miss Neha has written, in case of rocky region where the water is not able to percolate, what can be done to increase groundwater level? See, in rocky region, we call it, in terms of geology, we call it either hard rocks, and that can be granite or basalts. So in nature, nothing is continuous and nothing is constant. Wherever we have rocks, we have bedrocks or hard rocks, they are broken at places. There are fractures due to stress or weathering by rainfall, temperature, or their any region, maybe because of erosion by wind. So they are broken. So the best part to locate or to identify the water zones is to locate those fracture system, because they are the pathways. In critical zone, the soil, root zone, and the soil thickness is the pathways, but in rocks or in bedrocks or in hard rocks, these fractures are the pathways. So if we can locate them, then we can divert our recharge or divert the excess water through those fractures, and it will reach to the water table. Miss Neha, is it okay?
She's responded. Any other questions that the teachers have?
I was expecting a lot of questions to me.
I'll wait for everyone's question before I ask one that I have, but I'll wait for. Okay, I think I'll ask the question then. So, Dr. Tanvi, we, various parts of India, everybody's joining us from. And in terms of groundwater, we hear that we don't have sufficient groundwater. Now, where there are cracks, of course, we are aware that the water seeps in and then comes under the water table and the groundwater is formed. However, in all instances, it's very hard to know where the groundwater is at a good level and where it's not. So as individuals, and for me, what measures can I take, for instance, in order to increase that level of groundwater? Finding where there is a crack or a crevice where water may seep through might not be the easiest. Is there something that we can probably do on an individual level to make sure that we add on to the level of groundwater?
Yes, definitely, because every resource counts. And in the starting of my presentation, I said that water resource is like a bank. No, if you give input to it, then only we will have some output. And unless we deposit some money, we cannot draw the money out of it. See, finding cracks or getting recharge structures may definitely, it's not an individual's choice of work, and it's not possible also. But on an individual level, you can at least, means anybody should try to minimize the use of water. Many government campaigns are running that you should save water, you should while bathing or while drinking, you should store rainwater. But as a responsible citizen of the country, we should check, and I think it should be mandatory that all of us in our houses or in our buildings or in our sports complexes or even in malls, we should have the recharge pits. At least whatever rainfall is happening on the roof surface or on the terrace, if it is drawn down collectively to a certain extent through proper recharge pits, then it will not solve the problem immediately, but it will add on. And individually, see, suppose in your locality you have 20 houses, and each 20 house has that pit, a recharge pit on their individual terrace, and it is adding to a common point. Then over a period of time, not immediately, maybe after 2 hydrological cycle or after 3 years or 4 years, definitely water table will come up in that area. If not that, then in somewhere else. So it is not a one day investment that we can do, but definitely, yes, we have to somehow monitor the storage and take measures to minimize the usage of it. That I think on individual level we can do. And getting constructed the recharge pits is not a very expensive affair. It just need individuals' efforts. Yes, I want it in my home, or at least collectively 5 houses have one recharge pit, and then they can now very innovative recharge pits are coming. We can get beautiful flowers or plantation done over it. So it gives a very sense of satisfaction. Yes, we are using it, and then we are also seeing the life coming out of it. So that can be done, but it is more of an individual, it is a collective responsibility, but somebody has to start up.
Indeed, indeed. I'd just like to add that Dr. Tanvi, the award that she got, the Craig J. Beasley Award that she got, was for her contribution in the field of groundwater studies and its societal application. So it'll be whatever in our individual capacity, maybe as a street initiative or perhaps as a community initiative, if we can do even in little bits, I think it goes a long way, although it's a drop in the ocean, no pun intended, but little efforts will go a long way in making sure that we are taking care and making sure that water is used wisely. All right, so I guess there are no more questions. So what I'd like to perhaps do before we conclude for the evening is, in terms of next steps, there is a survey which is to measure the scientific attitude among school children. And this survey is in the form of a Google form. The link will be shared with all the teachers. If you could kindly share it with the students, they will be able to take the survey. It is a 30 question or so survey, and will not take any more than 5 to 6 minutes to do. This survey, as I said, is a measurement of the scientific attitude, just to see how this will help in identifying the gaps and challenges towards the scientific attitude of the school children. So in essence, it'll help in the development of a module or a mechanism to inculcate the scientific attitude. As we have seen, science is indeed everywhere, even on the earth and in terms of water. So that link shall be sent to all the teachers, and kindly pass it on to the students who may take the survey. So just to sort of, before we conclude, reminding all the teachers that are on the call and the students as well, that our next webinar is scheduled for the last Friday in July. It will take place on July 29, 2022 at 4 o'clock, same time, last Friday in July. Details, of course, as usual, we will share later. So since there are no more questions, Dr. Tanvi, cannot thank you enough for the time. We all learn something with every webinar, and it's fascinating to learn the real life applications of science. Physics was not one of my strong subjects, and I used to wonder where we would be using all those electrodes and how is the real life application of those. Of course, there are several, but it helps put things in perspective for every student. So thank you so much for taking the time, Dr. Tanvi. And I think that is about all. Dr. Farhat, Dr. Suman, any comments before we conclude?
Yeah, thank you, Nina. And I must thank from bottom of our heart that we have Tanvi here. And being a CSIR member, I was not even aware that we have such a great asset with us. So you're an asset to CSIR, of course, and to the nation also, because you're doing a marvelous job, Tanvi, I must tell you. And you have been doing such great work. So what I was thinking, we'll just catch up together sometime later, and we can just find out from your findings where we can put in something, add value to our policies. As you said, that innovative recharge pits can be a good thing. So let us make out a proposal or something like that, wherein, like, from your experiences, we can have some at least policy which we can give to our nation, and we can improve the condition of water tables and the scarcity of water which we are facing right now. So it will be a great contribution from your side, and I hope we'll be working together. And I'm so happy because our idea of inculcating scientific temper. In fact, when I saw your presentation in the morning, I was thinking maybe I don't know how kids will understand. And you made it so simple. You made it really so simple. Even like I said, even a non-scientific person can also understand what all you told, because you related with our day-to-day things happening, what we are facing right now regarding water. So I really thank you so much being here, and I thank someone also that because she suggested your name, and it's really great to have you. And in future also, we'll be expecting a lot of good work. Thank you, USO, and the whole team also for your so much hard work, and really thank you all. That's from my side.
Yeah, in fact, I should be thankful to all of you for me giving me a place to get connect with so many students and with so many teachers. And the patience coming from the teachers is really commendable. After their full days of work, they could spare more than an hour of time to be with us. And I am at NGRI. You all can get our contact details from any of the sources, whoever you know, and or you can just Google the name out and just try to approach me or our director or our team, and we will see how best we can be of help as a scientist or a researcher or a layman. So thanks to all of you. I'm really honored.
Thank you so much. Thank you.
Thank you, Dr. Tanvi, for a wonderful lecture. It was so simple. I mean, you made the complex things so simple. Even I had that fear of physics and all those things, but it was so, I mean, well explained by you. And yes, of course, students and teachers must have benefited by this. And thank you so much. Thank you, Ms. Nina. Thank you to all.
Thank you.
Thank you to everyone who joined in, and for the teachers, just pasting the link of the survey in the chat box as well. This will, of course, be shared via email and WhatsApp messages, but just putting it there for you also. All right, great. So thank you all very much. Have a great and wonderful evening. If it's raining, then a cup of tea on me. And we'll see you next Friday.